since its founding in 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests. I think you have to turn that down. To tonight's lecture by Juan Maldacena in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on the PSW Science YouTube channel. We will begin with a few announcements, a reading of the minutes of the 2395th meeting on aeronautical beginnings. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who has asked to remain anonymous. Please also join me in thanking the sponsor of tonight's lecture, our very own PSW member, Carl Merrill, sitting here in the front. Carl is a man of many interests and accomplishments. Aside from having been the first to introduce prokaryotic DNA into a eukaryote, in a manner of speaking, he invented the very sensitive silver stain method for visualizing biological macromolecules, and he is working currently to develop antibacterial therapies based on bacteria's natural enemies, the bacteriophage. He's also something of a car specialist. He's very interested in Ferraris. In fact, he collects them. And he also has a deep interest in physics, having done a double-slit experiment in his own basement. He wanted to know if you could change what happened after it happened. But I don't think he was successful as yet. And thank you, Carl. I'm pleased to announce that the following new members have been elected to the Society. David Rabinowitz, a faculty member at Oregon State University. He is a returning member with wide-ranging interests in science. Quincy Washa, a graduate student and Marine reservist, interested in early modern science, theoretical physics, and cosmology, who comes to PSW through the PSW meetup. Shahid Aslam, a space scientist at NASA Goddard, who comes to PSW through a colleague at NASA. And tonight's speaker, Juan Maldacena, whose background and interests will be clear to you in part from tonight's proceedings. Please join me in welcoming them all to membership. Any of our new members here tonight are invited to pick up a signed reprint of Volume 1 of the PSW Bulletin. And if you did not already get one, please see me after the lecture. Recording Secretary James Heelan will now read the minutes of the 2395th meeting and the lecture by Jim Green on aeronautical beginnings, delivered here at the Cosmos Club on September 7th.
Thanks, Larry. Good evening. On September 7th, 2018, President Larry Milstein called the 2395th meeting of the Society to order at 8:01 p.m. in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker of the evening, James L. Green, chief scientist at NASA and Civil War historian. His lecture was titled Aeronautical Beginnings, the Science of Ballooning During the Civil War. In the first half of the 19th century, ballooning technology in the United States conducted atmospheric research. PSW founder Joseph Henry was amongst those most interested in receiving and analyzing atmospheric measurements. By the end of the 1850s, aeronauts, people in balloons, were setting distance records in balloons filled with illumination gas distilled from peat. In 1859, John Wise and John LaMountain wagered they could balloon across the Atlantic Ocean before the telegraph was able to connect North America and Europe. Unfortunately, their balloon was destroyed during a test flight. Around that same time, Thaddeus Lowe was working to construct a 725,000 cubic foot balloon that could lift 22 tons. However, the gasworks in New York City was inadequate to fill the balloon. In early 1861, Lowe sought Henry's guidance and set to work on a smaller balloon to prove his design principles. On April 12, 1861, war broke out. At the same time, James Allen joined the 1st Regiment out of Rhode Island under Major General Ambrose Burnside and brought his own balloons to the regiment. In the following months, Allen conducted stationary ascents in Virginia for reconnaissance purposes. On June 18, 1861, at Henry's invitation, Thaddeus Lowe demonstrated ballooning for President Lincoln. Lowe conducted a tethered ascent on the National Mall, where the Air and Space Museum is now located. From his balloon, 500 feet in the air, Lowe telegraphed a message to the president, which Green calls the first message from space. That same month, General Benjamin Butler invited John LaMountain to balloon at Fortress Monroe in Virginia, where he successfully observed Confederate positions from tethers to land and to the USS Fanny. At the same time, the Union Army's topographical engineers called John Wise to service in time for the first Battle of Bull Run. Unfortunately, an inexperienced ground crew popped Wise's balloon on its way to the front. At the president's insistence, the Union Army subsequently established a balloon corps, for which Lowe was appointed chief aeronaut. Lowe's first order of business was to construct a total 7 new balloons in 4 different sizes, for which Lowe hired Allen, LaMountain, and additional other aeronauts into the balloon corps. Lowe then designed and constructed mobile gas generators to inflate balloons with hydrogen gas, which were able to remain inflated for several weeks. Further, inspired by LaMountain's use of the USS Fanny, Lowe converted a coal barge named the George Washington Parke Custis into a floating flat-top balloon tether that deployed to the Potomac River to observe Confederate forces on the Virginia shore and inland. Lowe's balloon corps eventually flew more than 3,000 times. Its duties included distribution around the city of Washington, using cadmium lights at night to maintain constant surveillance. In 1862, the balloon corps was also deployed during the Peninsula Campaign, which began in Hampton Roads, Virginia, after the ironclad duel between the USS Monitor and the CSS Virginia, formerly the Merrimack. General George McClellan intended to land 90,000 Union troops on the peninsula between the York River and the James River, but the CSS Virginia posed a threat to that plan. The balloon corps thus deployed at Fortress Monroe to observe the waterways for any sign of the Virginia, which never appeared. The balloon corps then stayed with McClellan's campaign and were deployed and provided valuable aerial intelligence at the Siege of Yorktown, the Battle of Fair Oaks, the Battle of Gaines's Mill, and during McClellan's evacuation from the peninsula. General Burnside subsequently deployed the balloon corps at the Battle of Fredericksburg. But, Green said, Burnside erred by sending inexperienced aides rather than aeronauts into the balloons, and failed to make use of their intelligence during the battle. General Joseph Hooker also deployed the corps during the Battle of Chancellorsville in 1863, but also failed to ensure stable lines of communication to use aerial intelligence. Lowe departed the corps after Chancellorsville, and according to Green, administration of the balloon corps fell apart. The Army placed the corps' balloons in storage until April 1864, when the Army sold 6 of the balloons and other corps equipment at public auction. Henry arranged for Lowe to obtain the 7th balloon as a settlement of his accounts with the Army. President Milstein then invited questions from the audience. One member asked whether any Corps balloons had any hydrogen-related accidents. Green said the Corps took many fire-related precautions, and that although the balloons were regularly hit with gunfire, the only accident in a manned balloon was a large tear caused by extreme weather. A guest asked why the Corps was always deployed near water. Green said that fast-moving water was required to cool the hydrogen gas coming out of Lowe's mobile generators to fill the balloons. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:11 p.m., President Milstein adjourned the 2,395th meeting of the society to the social hour. Temperature, 22 degrees C. Weather, thunderstorms, attendance 64. Respectfully submitted, James Heelan.
Can you take the reserved seats thing off and then tell the people there's seats in the front? Thank you, James. Are there any corrections or comments on the minutes? Seeing none, I will entertain a motion from a member to accept the minutes as read. The second from a member. All members in favor? Aye. All members opposed? The minutes are accepted as read and will be posted to the PSW Science website in due course. The 42nd meeting of the Society was held on Saturday, February 15th, 1873. President Joseph Henry presided. The bulletin reports on 3 presentations at the meeting. Mr. E. Foote read a paper on the laws of condensation of... I guess maybe they don't want me to hear this. Pardon me, short break here. It's been a long day of many technical difficulties. This one is easy to solve. It's called remember to plug your computer in. Well, it will take a while for it to get some power back, so I'll proceed without it. Oh, we're in luck. Okay. The wonders of electricity. So, Mr. E. Foote read a paper on the laws of condensation of aqueous vapor in the atmosphere, as a subject of very intense interest today. There's nothing more in the bulletin on this presentation, unfortunately. Eliza Foote was a lawyer and a judge and a mathematician and an inventor. He was among the founders of the PSW. He served on the Board of Appeals of the Patent Office and actually was the 11th Commissioner of Patents. Of perhaps even more note, he was married to Eunice Newton, a notable scientist and civil rights activist. She did early work on atmospheric heat absorption and emission, including some of the earliest work on the effects of water vapor and CO2 on warming in the atmosphere by the sun, that is, on the greenhouse effect. Some of this work was presented for her by Joseph Henry at the 1856 meeting of the American Association for the Advancement of Science. Mr. C.E. Dutton presented a memoir on the causes of the elevations and the subsidences of the Earth's surface. We don't have information on the contents of this talk either. Dutton frequently contributed to the early meetings of the Society. He served in the Union Army, ending his military career as commander of the arsenal at San Antonio. Primarily, he was a geologist and is especially noted for his explorations of the Colorado Plateau region. His USGS survey party famously towed a half-ton survey boat over the mountains surrounding Crater Lake and then down the steep 2,000-foot incline to the lake's surface. Their estimate of the lake's depth, carried out using piano wire and lead weights, is remarkably close to today's sonar-based estimate, 608 versus 592 meters. Dutton was a particularly fine writer. Wallace Stegner called him the poet of the Grand Canyon, and Dutton served as PSW president in 1890. Mr. Joseph Henry delivered the first of a series of discourses on atmospheric electricity. As I've mentioned in numerous past lectures, Henry was the preeminent American physicist and scientist of his time. He served as founding secretary of the Smithsonian Institution and founded and guided many important institutions of science besides it. He did seminal work on electricity and magnetism, especially on induction, and the fundamental unit of induction, the Henry, is named for him. His work had many practical applications and led to the invention of the telegraph. He was the founder, first, and still the longest-serving president of PSW. And I think we might hear something more about Henry. No, that was the last lecture. There was considerable interest at this time in the auroras that appear in the sky, and they were the subject of several earlier presentations to the Society. Henry, of course, would have been greatly interested in electrical phenomena in the atmosphere. As we heard at the last lecture, he was very interested in ballooning and played a role in early efforts to use balloons as observation platforms for military and other purposes. Perhaps he combined his interest in electromagnetism with his interest in ballooning to make aerial observations of electrical properties of the atmosphere. And with that, we turn from the past to the present and to tonight's lecture on black holes and the structure of space-time. It's my pleasure to introduce tonight's speaker, Juan Maldacena. Juan is the Carl Feinberg Professor of Physics at the Institute for Advanced Studies in Princeton, New Jersey, where he has been since 2001. Before joining IAS, he was a professor at Harvard University. Juan works primarily on quantum field theory, quantum gravity, and string theory. He's well known to theoretical physicists, particularly for proposing a duality between quantum field theory and gravity, relating gauge fields, strings, and quantum gravity. Among other honors and awards, Juan is a MacArthur Fellow and the recipient of the Einstein Medal, the Lorentz Medal, the Dirac Prize, the Heinemann Prize for Mathematical Physics, the Boucher Award, the Pius XI Medal, and the Sackler Prize in Physics. Juan was born in Buenos Aires, Argentina. He earned a BS from the Instituto Basirio in Argentina, and a PhD in physics from Princeton University. I apologize for my mispronunciation. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Juan to the podium.
Here I am. Thank you. Well, it's a pleasure to be here. Thank you for the kind introduction. So today we'll be talking about black holes and the structure of space-time. This is a small outline of the talk, so we'll discuss what black holes are. They are a solution that Carl Schwarzschild found of the equations of general relativity. And black holes were always very confusing. So Einstein himself was confused about black holes, and almost everyone who worked on black holes was confused about them. So don't feel bad if you're confused. I'm also confused. Then it was discovered, so Einstein thought that black holes could not exist, but then it was discovered that black holes are actually unavoidable. and a consequence of general relativity. The very big stars will collapse into black holes. Then it was even discovered that they are not black. So we'll see that there could be black holes that are red, black holes that are white, etc. And not only that, but that they imply that quantum mechanics is incompatible with gravity. That's what Hawking thought. And now we understand through some theories called string theory that black holes as seen from the outside seem to be compatible with quantum mechanics, and we can find an interesting relationship between quantum mechanics and the structure of space-time. So that's where the title comes in, about black holes and what they teach us about the structure of space-time. But there are still several puzzles that we're confused about, so the confusions still are present. Okay, so let's start. I normally start these talks with some more introductory remarks, some more basic things, and then we'll get more complicated. So I was told by the president that this was too elementary when he saw my first transparencies, so I apologize about that. But you all know the principle of relativity, invented by Einstein. Oh, no, wait, Galileo. Galileo invented the principle of relativity, which says that an observer traveling with constant velocity sees the same laws of physics as someone at rest. So here we have two observers. One is in his own lab, and the two labs are moving relative to each other. They move with constant velocity. No one can tell whether they are moving or not. And of course, we experience this every time we travel in an airplane and so on. What is the new thing that Einstein said? So Einstein went with the same idea, the same principle as Galileo, but there was one more thing, which is that the idea that there is a maximum velocity for signal propagation, the speed of light, and that velocity is the same for everyone, for all the observers. So for example, we go to the same two observers we were talking about before, and if I asked you which one sees the light traveling faster, you probably would say that this guy sees the light traveling faster, right? That would be our intuition from our everyday experience. But when you actually go and do the experiment, you find that both observers see the light traveling at the same speed. So that's an experimental fact, and that's Einstein put that in as a principle. And from this, he understood that the only way this can be compatible, so it seems unintuitive, and the way this can be compatible is that time flows differently for this observer. So the rate of time flows more slowly for the observer that is moving relative to this one, if these two compare their clocks. So for example, this leads to the famous twin paradox. So you have two twins that are born at the same time. One travels fast and then returns. And then this one, the one that travels fast, will be a bit younger. Okay? So that's how things are, and when you can do these experiments with elementary particles, and you can indeed check that this is true. So it's weird, but true. Now you might say, well, which of these two twins? I mean, the two twins traveled, and which of the two twins is the one that becomes younger, right? And the thing is, the two twins are not exactly equivalent in this experiment. So this twin here did not feel any particular acceleration. He always remained at rest. This twin felt some acceleration when he was moving, accelerating to move away, and then some acceleration when he was coming back. And so the one that felt some acceleration actually is the one that is a bit younger. So they're not completely equivalent. Now, imagine that we are going to run the following experiment. So we have two twins. One will travel and the other one will not, as before. But when they meet, they have to die. Okay, that's the rules of the game. So sorry for the game. It's a little macabre. But, now, the question is, which of the two twins would you rather be? Yeah, the one that stayed at rest, right? And the one that was traveling with constant velocity, zero velocity in this case, and not the one who was accelerating, right? Now, it turns out that, yeah, you would rather be this one. And that's even true out of elementary particles. So elementary particles also have this preference. So elementary particles are like these twins that prefer to extend as much as possible their own lifetimes. There is a principle of somehow maximal lifetime for particles, or maximum proper time. And that's a principle of physics. It's one of the laws that governs how particles move in a given space-time. And that's the reason, essentially, they like to move with constant velocity, unless there is some external influence. So that's a principle for the motion of particles. So they try to maximize their experience time. Now, so part of the lessons of special relativity is that the way two observers perceive space or time can be different, but they both perceive a complete unity, which is space and time. That's why we talk about space-time together, and we join them in a single word. So space and time is the union of space and time. What is space, what is time, depends on how you are moving, but the totality of both is perceived the same way by both. How we perceive time depends on how we move, and another property is that particles tend to move, well, particles will move in a straight line trajectory through that space-time. Straight line means with constant velocity. And they do so in order to maximize their lifetime. Okay, so now we talked about space-time and special relativity. Now we'll talk about something that at first sight looks like a different topic, which is gravity. So I guess Galileo had the idea that heavier objects fall faster, but Galileo then realized that everything falls in the same way once you remove the effects of air resistance. And this led to the so-called Einstein happy thought, which is he realized that when you are falling freely, so if everything falls in the same way in a gravitational field, if you were falling, let's say you are on a, imagine you are sitting on a scale, so you are weighing yourself, but you are falling together with the scale, then the scale would register zero weight. So the idea is that gravity disappears when you are falling freely. He also used the metaphor of an elevator. You're falling in an elevator. Now, he promoted this into a new law of physics, which is the idea of the equivalence principle. And the equivalence principle basically says this, that when you fall freely, gravity disappears. And, well, we have these famous pictures of the astronaut and the spaceship. Both fall in the same way in the gravitational field of the Earth, and the astronaut feels he's floating in space. Now, Einstein, with these ideas, developed the theory of general relativity, which is the idea that gravity is due to the geometry of space-time. So the basic idea is that the geometry of space-time is not flat, not rigid, but it's dynamical, it can change, and if you place a heavy object in space-time, space-time gets deformed a little bit. And then when you have a particle that moves in that space-time, the particle will move not in a straight line, but in a line that maximizes the proper time. Again, maximizes their own experience lifetime. That's the principle that determines how a particle would move in space-time. So if we had a spatial analogy, we would say that space is like a curved surface, and a particle will follow the trajectory with minimal length in that space, in that surface. But what the particle is really doing is it's maximizing its own lifetime. So here we have a little picture of the Earth deforming the space-time around it, and a particle going around. Now, so one of the things that this implies is that gravity changes the flow of space-time, the flow of time. And so I'll give you an example of how this works. So imagine that you live in the bottom part of a building, and your friend lives in the top part of the building. So you each have two identical clocks made exactly of the same material, or the same design. Then you find that the clock on the bottom part of the building runs a little more slowly than the one on the top part of the building. Okay? So time runs faster for this one will age a bit faster than this one. Okay? So if you want to not to age too much, you can go into the bottom top of the building. Of course, it's a very small effect. It's 1 part in 10 to the 15. But there are clocks that people make, especially in Colorado, in the National Institute for Standards. They make really precise clocks that can detect 3 centimeters difference in elevation. So here we can also have the same twin paradox. So if we take 2 twins and we hold one of them near a very massive body, this one will age a little less. Okay, so when Schwarzschild found the solution, so Schwarzschild took the equations of Einstein for general relativity, and he asked himself, what is the shape of the geometry outside a massive object? So he didn't find the geometry everywhere, only the geometry where there is no matter. So the idea is there is some matter here that causes space to be deformed, and then he says, well, what would be the total result of that deformation away from that matter where there is no matter? And he found the shape of the space-time. And this is the shape of that four-dimensional space-time. It's very far away. It's very close to the standard flat space, similar to well, it's the kind of space-time we have in special relativity. But as we get closer, we have a deformation. And one of the things that this space-time is telling us the rate at which clocks move. Okay. So, for example, we have some clock that is far away, it's running at a certain speed, and then when you are closer to the massive object, the clock runs a little more slowly. So this one is running a little more slowly than this one. And also this observer who's sitting here at a fixed distance from the star is feeling some weight. So if he sits here, would feel some weight. Now, imagine you have the same star with the same mass, and you make it a little smaller. So you make it a little smaller, so the star will be a little smaller. The person here will feel more weight, and the clock will run more slowly than it was running when it was here. And it turns out that the geometry that Schwarzschild found is such that if the star is smaller than a certain amount, then it looks like the clock for someone who's sitting at that fixed position would seem to stop completely. Okay? And the person here would feel infinite weight. Okay? Does this sound reasonable to you? No? If it sounds reasonable, then I'm not explaining it clearly enough. This should sound very unreasonable. It was very unreasonable for Einstein, so you're not alone in feeling this is unreasonable. And he thought that this could not happen, that matter could not be contracted so much so as to lead to this conclusion. So Schwarzschild might have found this solution. It's a mathematical solution, but it's not what physically actually happens. Okay? That's what Einstein thought, and you're perfectly entitled to think that. Now, something important about this observer that feels infinite weight, right, is that he's not falling freely, right? He needs, if you're sitting at some distance from the star, you need some rocket, right? You need someone, or you need a rope tying you to some place far away to prevent you from falling into the star, okay? So they are not falling freely. Now, Einstein's principle said that if you are falling freely, gravity disappears, okay? So what would happen if this person here decides to fall freely? So forget about the rocket, forget about tying yourself to a rope far away. You just fall freely. Okay? Now, you can calculate what would happen and what this person would feel using that solution that Schwarzschild found. And what happens is that the space-time continues beyond that surface of infinite, apparently. So that surface where you would feel infinite weight if you were staying stationary is called the horizon of the black hole. And a person that just falls through the horizon, and nothing special is felt when he or she falls through the horizon. Then deeper in the interior, the geometry of the black hole looks like a time-dependent geometry. It looks like a collapsing universe. It looks like the whole universe is collapsing around you. And eventually you get to a big crunch here, singularity, so a region where the whole space-time shrinks to a very infinitesimally small point. So we have something like a little, the opposite of a big bang inside each black hole. You have a little big crunch. Now notice the singularity here is not sort of in the interior of the black hole in the sense that moving inside, but it's to the future of the horizon, right? It's in the future of that region. And it's hidden from the outside, so if you fall in, you cannot send the signal to the outside because trying to go to the outside is similar to trying to go to the past. So you cannot send the signal to the outside for the same reason that you cannot send the signal to the past. Okay? So that's why it's useful to think of the singularity as being into the future. Now, an analogy that, that is sometimes made for this is the following. So we can think of space-time as a river. And imagine you have a river where the velocity of the water is slow in this region, and then it becomes larger and larger and larger, and then here you reach a waterfall, and you fall into the waterfall. Now imagine that in this river we have some fish, and the fish can travel at some velocity, can swim at a certain velocity, and if the velocity, let's call the velocity that of the fish can swim, c, this stands roughly for the velocity of light, so it's analogous to the velocity of light. And then if the velocity of the water is less than the velocity of light, a fish swimming to the right will manage to avoid falling into the singularity. If there is a place where the velocity of the water is equal to the maximum velocity, to the velocity at which the fish can swim, and if a fish swims here, it will stay stationary here and it will not move. And that's analogous to the clocks stopping at the horizon of a black hole. And finally, if a fish gets in here, the fish can try to swim to the right, but the fish eventually will fall into a singularity. Now, if the fish is swimming in this river, and the river, let's say, is muddy, and the fish cannot see the coast, the fish has no way of telling where the horizon is. Okay, so that's why the fish does not feel anything special when it is crossing the horizon. Okay, so we learned a few things. I reviewed for you a few things. So one, the black holes have this surface we call the horizon. Once you cross it, you cannot get out. Then it was understood that stars can collapse into black holes, and that also there are objects in the sky that seem to be black holes. So let me tell you a little bit about real black holes. So these are produced by collapse of massive stars, and they have a size of order from 10 to 200 kilometers roughly. And there are also black holes at the center of galaxies, which are much bigger. They have sizes comparable to the size of the solar system. So how do we see them? So we can see them because sometimes there is matter around the black hole, and when there is matter around the black hole, they heat up, they become very hot. It becomes very hot as it's falling to the black hole, and we can see that light or radiation that that matter emits. And a new technique is now that we can see gravity waves when two such black holes collide. So this is an example of a black hole at the center of a galaxy. This is an actual picture, so a combination of an optical picture. Here is the galaxy and some radio emission from some jets of particles that are coming out of the black hole. So there is matter falling. In this case is one of these cases where there is matter falling into the black hole, and some of the matter sort of bounces back, and we have this emission, and that's how we see the black holes. And it's believed that many galaxies similar to ours have these black holes at the center. I mean, the black hole is very tiny, so that is the size of a solar system, which is much smaller than 400 light years. Right? And the new way we have now of seeing black holes, it's a great way actually, is the following. So two black holes could collide with each other, and in doing so they emit gravity waves, and they can be seen by the gravity wave observatories that people have built. Two detectors here in the US, and there is one in Italy now that is there. All three of them are detecting these gravity waves, and they've detected a few events like this. And this is great evidence of the collision of these black holes. And the way you test this idea is that you can calculate the shape of these gravity waves according to the equations of general relativity, and then compare to the shape of the waves that you see here on Earth, and they seem to match pretty well. So that's and in the next few years there will be many experiments in these directions, and we'll get better and better picture for what these black holes are like. So this is the end of sort of my experimental part of the talk, where I show you some of the evidence that we have black holes in the universe. Now I'm going to tell you about some interesting theoretical properties that black holes have. Why? So some fun and interesting properties of black holes. And that give rise to some interesting conceptual questions. So one interesting property is that the final shape of a black hole is independent of how you form it, right? So there are many objects in nature. So a star, for example, if you look at stars in the universe, there are some stars that are of different colors. There are red stars, there are more bluish stars, and so on. If you were to collapse those stars into black holes, they would all basically look the same if they have the same mass. There is only one parameter, basically, which is the mass. And also there could be some rotation velocity. So if they all collapse, they form a black hole. Here I cheated slightly because these are all pictures of the sun, but anyway. So that's an interesting property. So they're very universal and very simple. They are characterized by only two parameters, the mass and the angular momentum. Now the other thing that is simple about them is the following. Imagine that you have two black holes that collide. When they collide, as we saw, they emit gravitational waves, and we indeed have detected these gravitational waves. And they form another black hole. Now the question is, first question is whether how is the mass of this black hole related to the mass of these two black holes, right? So we have two black holes with some mass m1 plus m2. When they collide, they can form a black hole that will it have the sum of the masses of the two, or will it be smaller than the masses of the two? Yeah, so many people here are saying that it will be smaller. And it will be smaller because the mass is the content of energy of these black holes. And when they collide, they emit gravity waves. So part of the energy is carried by the gravity waves. And so there is less energy left to form the black hole. And so the mass of this black hole will be smaller than the masses of the initial black hole. And so one question that was asked, people were wondering, was whether maybe this black hole completely disappears. Everything is emitted into gravity waves. Maybe that could happen. But it was found actually that even though the total mass decreases, the area of the horizon always increases. So no matter how you collide these black holes, where they are rotating or not rotating and so on, the area of the horizon is always bigger than the sums of the initial areas of the horizon. And so this is a very simple property that follows from the complicated equations. So the Einstein's equations are sort of mathematically elegant, but very difficult to solve. Only, let's say, in the last 10 years, people have understood how to solve the equations on a computer in an efficient way. And so that's when you find an interesting property, an interesting simple property like this, you always are happy about this. And this property constrains the amount of gravity waves that you can emit. And this is something that Hawking discovered. Now, so far we discussed black holes according to Einstein's theory, which is classical theory. But when we include quantum mechanics, we find a new surprise. And the surprise is that we can have white black holes, as I already said before. So the idea is that the laws of quantum mechanics imply that black holes can emit some radiation. And this is called Hawking radiation because Hawking was the first to understand that black holes would do this. This is a theoretical prediction. It has not been tested experimentally. It has not, because the black holes that exist in nature are very big, and they would emit an amount of radiation which is very, very small, and so cannot be seen. But the idea is that the temperature of the black, so they emit radiation at some temperature, they emit radiation like a black body, and as you decrease the size of the black hole, the temperature becomes hotter. So a small enough black hole will look white. Okay. So here I've listed the temperatures of various black holes with different masses. So for example, if you had a black hole of the mass of the sun, which are the types of black holes that can be made in nature, the temperature is very tiny. So this is many, many zeros, degrees Kelvin. Okay, this is super, super cold. It's colder than the temperature of the cosmic microwave background, so you cannot see this. Now, if you had a black hole that had the mass of a continent, and you made such a black hole, it would have roughly the size of a bacterium, which is also roughly the size of visible light. And a black hole of that size would actually look white. Would be a very tiny little white dot, and you would actually see it white. So, and you would even be able to see it with your own eyes. Actually, in some previous incarnations of this talk, I actually made a little LED that would emit this amount of light. And I turned off the lights of the auditorium and so on. We'll not do that today because it's a little underwhelming. The people in the back don't see anything, and then they are not impressed by the powers of black holes. But, if I were to actually make an honest black hole that had the mass of the continent, you would not survive it. So it's good. So there will not be any demonstrations with black holes today. Now let me give you a little bit of why black holes emit thermal radiation. So this is a little bit of a cartoon of an explanation. Yes. Oh no, I this is just to keep people awake. Yeah. So in relativistic quantum mechanics, particles are not conserved. They can be created and destroyed. And in particular, in the vacuum, you can have pairs of particles that are created. And when this happens, one of the particles has positive energy, and one of the other members of the pair would have negative energy. And now, in flat space, there is a rule that says that any particle, any honest particle that exists, should have positive energy. Okay? And you can think of the vacuum as having a little bit of a policeman that ensures this rule. So the policeman that ensures that every particle, honest particle that exists, should have positive energy. But the policeman is constrained by Heisenberg's uncertainty principle. So if there is negative energy, but for a very short time, okay, the policeman doesn't have, cannot detect it. So it can happen. But so that can happen for a very short time, but you will not find a particle lying around for a long time that has negative energy. Now, the interesting thing is that in the presence of a horizon, the notion of energy is different for the inside policeman and the outside policeman. And that has to do with the distortion of the shape of space-time outside the black hole relative to the inside of the black hole. And so there is something that we call energy, which is the energy as measured from the outside. And from the outside, this particle has positive energy. And from the outside, this particle has negative energy. But for this policeman that is inside, what the outside views as energy, the inside views as something else, let's say momentum. And this can be positive or negative. So the notion of energy from the person inside is different. And so this policeman inside is perfectly happy with that negative, with that particle, and lets it exist, and it can exist for some time. And so this process can go on, and so you can have this negative energy particle going in and one positive energy particle escaping to infinity. And those positive energy particles escaping to infinity form the radiation that Hawking discovered. So Hawking discovered this radiation by doing a calculation which, well, has some of these elements, let's say. Okay, so this phenomenon implies that black holes have a certain lifetime. So they emit radiation, and they lose mass. And so if you had a black hole, it will start losing mass, and become smaller and smaller, until eventually it would disappear. And we call this process black hole evaporation. And the lifetimes of various black holes is the following. So if you have a very big black hole, like the mass of the sun or the Earth, it will take more than the age of the universe. If we have an ordinary black hole, it will evaporate, let's say, if you have a black hole with an ordinary mass, let's say a mass of, let's say, 100 kilograms, and you made it into a little tiny black hole, it will evaporate in a very tiny fraction of a second, and it would be an explosion worse than a nuclear bomb. Okay, so it can be very fast for very small things, but it can be very slow for very big black holes. And if you had a black hole that had the mass of a mountain, this 10 to the 12 kilograms, roughly the mass of a mountain, produced at the beginning of the Big Bang, then it would be evaporating right now. Now, we don't know whether those black holes were produced at the beginning of the universe. Probably not. There is no evidence that they were produced. But and also there are some theories where there could be very tiny microscopic black holes that could perhaps be produced in future particle accelerators, but those black holes would evaporate very, very quickly, almost as quickly as they were produced. Okay, so so far I've discussed a few issues that had to do with this interesting phenomenon that Hawking discovered of black hole evaporation, and now we'll discuss some problems that this phenomenon poses. So these thermal properties of black holes mix quantum mechanics and gravity, and this leads to a couple of puzzles. And I discuss two puzzles. The first one is why are black holes hot? And the second one, it's a little more subtle, is some problem about information loss. So first, when we are faced with the concept of temperature, for any system that has some temperature, we understand the temperature as due to the motion of the microscopic particles or microscopic objects that make the system. So if we have air in this room and we heat it up, then the molecules will move a little faster than when it was colder. And there is a related concept of entropy, which is saying in how many ways these constituents can be arranged. And the first law of thermodynamics gives us the entropy if we know the energy and the temperature of the system. And Hawking calculated the entropy as a function of the mass. And so from there, you can calculate the entropy. And it turns out that the entropy of a black hole is equal to the area of the black hole divided by the Newton constant and the Planck's constant, which this combination turns out to be a quantity with some size, some length, some elementary length, which is very tiny length, 10 to the 33 centimeters. It's sometimes called the Planck length. And so the entropy of the black hole is, for a macroscopic black hole, is very big because this denominator here is very tiny. So this Planck length is the length scale at which the quantum effects of gravity or the shape of space-time become very important. Now, one interesting feature about this formula is that this phenomenon that Hawking found by simply thinking about Einstein's equations, which are completely classical equations, that the area of the black hole increases, translates into the second law of thermodynamics, the idea that the entropy always increases. Okay? And that's quite surprising that Einstein equations somehow know about the second law of thermodynamics, because there is nothing statistical, nothing. I mean, no, Einstein didn't think about temperature or anything like this. He was just thinking about the perfectly deterministic equation. The question that this raises is, what are the constituents of a black hole? So for any other thermal system, we explain the entropy and the temperature in terms of some microscopic constituents. Somehow the atoms or the molecules or whatever is making up the system. And here, whatever is making up the system should be the microscopic constituents of space-time, because black holes are independent of the matter that formed them, depend only on the shape of space-times. In principle, you could even form black holes with gravity waves. So if you had gravity waves and you focus them in some region of space-time, even with no matter anywhere, you could still form a black hole. So the idea is that these microscopic constituents depend on space-time. And so that's why black holes, and especially these thermal aspects, are related to the very fundamental question of the basic objects that make space-time. So that was one of the problems. The second is the problem of information loss. So we said that a black hole can be formed in different ways. You can throw all kinds of information into a black hole, but at least in Hawking's approximation, the things that come out are thermal. So they have no information of the things that made the black hole. That's related to the fact that black holes have this universal character, that they always look the same. And on the other hand, in quantum mechanics, if you form something in different ways, the net result should always be different. The difference might be minuscule, might be very tiny, but there should always be some difference. And the question is how those differences come about. So there should be some subtle differences in the outgoing radiation. So in order to address these questions, to see what, I mean, this issue was the reason why Hawking said that the information could not come out. So Hawking said, look, the things went already into the black hole. There is no way that something is going to travel from the future to the past and send this information. You will lose information. That's what he proposed. But in order to see whether that's the case or not, we need really a better theory. We need a theory that puts together quantum mechanics and gravity. And that is this theory called string theory that some of us have been studying. So string theory is a theory under construction. It's a theory of quantum gravity that talks about the quantum mechanics of space-time. And it reduces to Einstein's theory under ordinary circumstances. By ordinary circumstances, I mean at long distances and for very big objects. And it can describe in a complete way certain simple universes with negative curvature. And I'm going to focus on only this aspect of this theory and nothing else. So, and so this relationship is sometimes called holography. It's the idea that we can describe the interior of certain spacetimes in terms of a theory that lives purely on the boundary. So the idea is that we have spacetime. This works nicely for spacetimes that have negative curvature. This is a little picture of a spacetime with negative curvature. It was made by a painter called Escher, a Dutch painter. And here you should imagine each of these fish as having the same size, the same proper size. And the reason they get smaller here is because they are because of the curvature of space. And we have projected that curved picture into the flat surface of the screen, and that's how they got deformed. I mean, you find a similar phenomenon when you take the surface of the Earth and you project it onto a plane, and then the regions near the poles typically get deformed with the typical projection. And in that case, they look bigger than they actually are. In this case, the opposite happens, look smaller, because the sphere is positively curved, this is negatively curved. And these spacetimes, you can think of them as having a boundary, which is after you project them onto the plane, there is this region very far away that, in this case, has the shape of a circle. And now the idea is that you have two ways of describing the same physics. One is that you can have, let's say, for example, particles or any object moving in the interior, and you have an equivalent description in terms of particles that are very strongly interacting and live on the boundary. Now, the interesting part is that the particles living on the boundary do not have gravity, so they don't feel gravity. They feel other interactions. The spacetime where they live is the boundary of this original spacetime that has no fluctuations, is completely rigid, and that's where these particles live. Here I have tried to represent the fact that they have strong interactions by this jiggly motion. So they don't look like classical particles like this. They are quantum particles with strong interactions. And those particles describe the same physics as some object that could be living in the interior. And the interesting thing is that even if you had a black hole in the interior, so suppose you have a black hole in the interior, then in this, we can describe it in terms of particles that move here on the boundary. So here I started drawing these particles, and I really got tired. And this should really look like a fluid of particles, a completely uniform fluid of particles that are very strongly interacting, and it's at some finite temperature. And the idea is that the temperature and entropy of the black hole is accounted for by the motion of these particles living on the boundary. And in some cases, we can calculate this very precisely and see that it agrees with the formulas of Hawking and Bekenstein in some very simple toy models for universes with these models that have negative curvature. So one answer to this question of where the atoms of space-time are that give rise to the black hole entropy, you can say, well, one way of presenting them is as these particles that live at infinity. They don't even live near the black hole, they live far away. We describe the whole space-time together with the black hole in it by this boundary theory, and those particles give rise to their entropy. And the theory on the boundary obeys the rules of quantum mechanics, so the black hole in the interior should also obey the rules of quantum mechanics according to this correspondence. So this leads to the idea that black holes are consistent with the laws of quantum mechanics. Now, this relationship might look a little strange. And if it didn't look strange, maybe it's because, again, I didn't explain it properly. And one thing that is strange is that there are particles that live on the boundary of space in some lower dimensional region, and they give rise to physics in one higher dimension. And I'm going to try to explain more or less conceptually how this is supposed to happen. So in order to explain this, I'm going to use a kind of verbal analogy. So the analogy is the following. So imagine that we take a sentence. So I took a random sentence. Let's say the sentence here is, if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. So take this sentence. And then I here wrote the same sentence. And then you start doing syntactic analysis. You start analyzing the grammar and meaning of this sentence. So when you heard this sentence, you did this analysis that I'm going to do here in your head to understand the meaning of this sentence. So you group the different letters into words, and then you group the words into bigger units, into little phrases. They have some names and so on. And then you have a bigger phrase, and then a second phrase, and so on, different clauses. There are also long-distance correlations between the words here. For example, the word man, his, and he are correlated. They're all related to each other. The concept here of keeping pace is related to drummer. So these are longer distance correlations between the words in the sentence. And for you somehow to understand the whole meaning of the sentence, you needed to go from these letters to these higher meanings and higher constructions. Okay? And the idea is that here we have a kind of extra dimension here, which is the dimension in which you are doing this analysis, of going to higher and higher scales in your analysis. So the idea is that in this analogy, the phrase is the state of a quantum system. So it's the wave function, or the thing that characterizes the state of the quantum system. And the geometry is doing a kind of analysis of that state and characterizing the correlations that we have in the quantum system. So at short distances here in the quantum system, we have lots of correlations. And then as you go to longer and longer distances, you have larger correlations. And so there can be correlations that propagate over a very long distance. And those are related to particles that propagate in the interior space-time. So the particles propagating into the interior are related to some kind of correlations that exist at very long distances between in the state of the quantum system. Now, the question is, what is a black hole in space-time? So imagine we go back to this sentence, and we start changing this sentence a little randomly. First, we change it just a little bit. So here I changed these few letters, right? So I change his by its, and he by she, and so on. So before we had some correlation between man and he and so on. Now we don't have it anymore. So we lost those particles we had in the interior. And the sentence makes a little less sense. So we can analyze this sentence up to the level of these phrases, but we cannot continue further. We say there is a kind of horizon here. Now suppose we change a little bit more the sentence, right? Now we say, if a man, my nice mother pays with, so this sentence makes a little less sense. But if you analyze little pieces of the sentence, they still make sense. So the sentence makes sense up to a certain level, but not beyond. So again, we say there is a horizon. The horizon has moved a little bit upwards. And then finally, imagine that you change all the letters randomly. Then the horizon went all the way to the boundary. It's the biggest black hole you could have in this space-time. So the idea is that the area of the black hole is related to the level of ignorance you have in this sentence. And if you start, the idea that the area grows, or the second law of thermodynamics, is saying that if you just start changing a sentence randomly, it's more likely that you're going to mess up the sentence and alter its meaning, may make it meaningless, and so the ignorance always will grow, right? So a very well-formed sentence is some very low entropy or very fragile thing that when you start changing it, you start messing it up. Now imagine that these changes that we have here, so let's say we start with the original sentence that made sense, and now we run it through an encryption algorithm. So an encryption algorithm is some rule that changes the letters in a way that looks random if you don't know what the algorithm is, right? And that's what computers do in order to send information through the internet. They change it so that if some thief wants to get your credit card number, he will see some random letters, will not see the number. Okay? And so in this situation, if you don't know the algorithm, you would say there is this is random garbage, and there is some big black hole in the space-time. Now, the idea is that if you know the encryption algorithm, then you can recover the original sentence, right? And the idea is that the laws of physics in the boundary are like that encryption algorithm. So the laws of physics are deterministic. Is some set of rules. All the laws of physics, including the rules of quantum mechanics, imply that, well, they change the state of the system in some way that you can then change it back to what it was before. So you can run it forwards in time or backwards in time. And so in principle, you can run it backwards in time and get the information that was contained in the initial black hole or whatever. So because those rules at the boundary are completely reversible. And so we can undo the formation of the black hole and in principle recover the original information. And so that's how you can think of black holes as compatible with quantum mechanics. Now there is these ideas of relating strongly interacting particles to black holes is useful for some other purpose. Imagine that you don't care at all about black holes. Imagine you are a condensed matter physicist or some person who doesn't care about gravity. But you might care about quantum systems that are strongly interacting. You might be interested in, let's say, in building some quantum computer that will have strongly interacting quantum particles and so on. And, or you might be interested in some fluid or some system that has these very strongly interacting particles. And then you can use this relationship to model those fluids. So you can replace, in some cases, some very specific systems, you can replace those fluids of very strongly interacting particles by Einstein's equations in a higher dimensional space. And then you can use the equations of gravity to solve the system you're interested in. So this is, in this way, people have analyzed some aspects of high energy collisions of very heavy ions that create new phases of matter, and so-called quark-gluon plasma or quark-gluon fluid. And you can use these black holes to analyze some aspects of these phases. OK. Now, I'm going to say a few words about entanglement and geometry. So I mentioned, when I talked about the verbal analogy, I said that the emergence of space-time is related to the correlations that you have in the quantum system. But in a quantum system, you can have a form of correlation which is called entanglement. And it's a very peculiar kind of correlation that you can have in quantum systems. Fortunately, I won't explain exactly what it is, but let me just say that it is similar to classical correlations, but a little bit stronger than classical correlations. And this property is important for the emergence of space-time. And the analogy was simply the same one that I gave before with the sentence. But so I will discuss only one example of this. And this is related, again, going back to the solution that Schwarzschild found. And now we'll consider the so-called full Schwarzschild solution. So this is a solution of a space-time that contains no matter. So before I talked about the star and the solution outside the star. So let's say we have the solution that originally Schwarzschild found had no matter anywhere. And when it was properly understood, and it took about 50 years to understand it properly, it was understood that that solution actually describes not one black hole, but two black holes. And this diagram attempts to represent that. So here in this diagram, we have suppressed two of the dimensions of the four-dimensional space-time, and we represent only two of the dimensions. The vertical direction is roughly time, and the horizontal direction is roughly the radial direction as you approach the black hole. Okay? And then in this type of pictures, light propagates at 45 degrees. So we deform the space-time geometry and we project it onto the screen, but always preserving the fact that light propagates at 45 degrees. So this region here, this square here in the outside, represents the exterior of a black hole. So that's what we've been talking at the beginning of the talk. So there is a horizon that is this, this light ray here. And if you go into the interior, you fall into the singularity. The horizontal line is the singularity, it's the big crunch that we talked about before. And then that interior is connected to a second exterior. So we have here another black hole, and they share a single interior. The two black holes are not connected to each other. They live in two completely separate spacetimes, and they share that single interior. And this is the simplest solution of pure Einstein gravity with no matter. Okay, so it's not some space-time that I cooked up before I come into this talk. Okay, so it's the simplest, the first solution that was found of general relativity has this funny shape. Now this is not quite the solution that you get when black holes form in nature, because in nature there is also matter. This is a solution without matter. So the question is, what is the interpretation of this solution? And for a long time, people said, oh, well, this solution doesn't make sense. There are two spacetimes. We should ignore it totally. But actually, this has a very interesting interpretation. So you can think of, there are solutions that are very closely related to the solution I just mentioned, where you have two black holes that are very far away from each other, but they are connected through the interior in the same way that they were connected in the previous solution. We sometimes call this connection, this blue line is sometimes called the Einstein-Rosen bridge. They were the first to realize that the solution had two sides. And sometimes we also call it a wormhole. So it's something where the space is connected between two distant. So if you can have a black hole, let's say here, and a black hole a million light years away. And if you stand here 1 meter outside this black hole and your friend stands 1 meter outside that black hole, you are separated by 2 million light years in space. But through the interior in this geometry, you are separated only by 2 meters. Okay? So in that sense, is that we have a wormhole in space. Now, as I said, if you find two black holes in nature produced by natural gravitational collapse, they will not be described by this geometry. This is a very special geometry, but it's a possible geometry according to general relativity. Now, I said that you were going to be 2 meters away from your friend. So you would be, let's say, at some instant in time, you're here outside. Your friend is outside at 2 meters away. However, if you try to fall in, you cannot travel faster than the speed of light, and you want to go to your friend, you try to go in, and you end up falling into a big crunch. So the universe collapses before you can go through this wormhole. So that's why these are called non-traversable wormholes. You cannot really go through them. And these are perfectly consistent with the laws of physics as we know them. And you cannot send any signals through this wormhole, and they don't lead to any causality violation. So you cannot travel faster than the speed of light. So they are not useful for science fiction. So the usual science fiction wormholes are those that allow you to travel faster than the speed of light. So I'm sorry to tell you that you cannot use these ones for that purpose. So the idea is that in the exact theory, each of the black holes is described by a set of microstates when we view them from the outside, a set of quantum states. And the idea is that geometry of the wormhole arises when you entangle the two states. So when you have the microstates of the two black holes and you put them in an entangled state, then you will generate that geometry. You'll generate that connected geometry. So you generate a connection in the structure of space-time when you entangle these two black holes. And some of us have speculated that perhaps it happens with any kind of entanglement, but that's a wild speculation, so I won't discuss it more. So we have this geometric connection from entanglement. That's why, and let me make a small analogy. So again, we go back to the phrases. So here we have the same phrase we had before, and here in the bottom we have the same phrase but in Spanish. Okay, and so the details of the letters are different in the two cases. But when we start analyzing the sentence, at some point we find some common structure. So we would have some kind of correlations that describe this sentence, and other kind of correlations describing this one. But at some point, the two collapse into a single semantic interpretation. Okay? And that's somehow the connected wormhole. Okay, I said that these wormholes are not good for science fiction. So let me tell you a little story. So it's a kind of science fiction story, but it's different than the usual ones. So let's say that we have two people. This is far in the future, so in a very advanced civilization. And we have this one called Romeo and this one called Juliet, okay? And their families don't like each other, so they keep them away. And they keep Romeo here in the Milky Way galaxy and send Juliet to the Andromeda galaxy, million light years away, okay? But they are very smart. They are really very smart. And they start sending each other entangled qubits, so entangled messages. So this one generates an entangled pair and says one to Juliet and so on. And this way, they accumulate lots of entangled qubits. Then they collapse into a black hole. This is far in the future where they really can control all this very well with very precise quantum computers. They can do all that, and they create two big black holes, one here and one over there, okay? One in the Andromeda galaxy. Now, I'm going to, now after they've done that, they decide to jump into these black holes, okay? So first look at the bottom part of this transparency. They jump into these black holes. Romeo jumps into the black hole, Juliet jumps into her black hole, and their families just say that they committed suicide, right? They just, and that's what the narrator of the story, who remained outside, also would say, and has said, actually. But that's not what they experience. So what they experience is the following. Now look at the top part of the transparency. So they actually jump into their two black holes, but because they've entangled them before, they created a geometric connection between the two black holes, and they actually meet in the interior of the black hole and can live there for a while. Unfortunately, in this version of the story, they die. But anyway, but there is a slightly more complicated version of the story where they don't die, but I don't have enough time to tell it to you. Okay, so we still find the black hole interior a little mysterious. We don't understand all the rules that describe the black hole interior. And we know the equivalence principle tells us that there should be no problem when you cross the horizon, but we cannot describe the black hole interior using the same variables that make quantum mechanics manifest for the observer outside. So there are still some mysteries. In summary, there are still some mysteries that we don't understand. So in conclusions, black holes are fascinating objects where the geometry of space-time changes in a dramatic way. Black holes and quantum mechanics give rise to very interesting theoretical challenges, and string theory can describe black holes in a consistent way, at least as seen from the outside. And one of the lessons, or one of the themes, is that space-time seems to be an effective concept that can arise from the interaction of some more elementary particles that live at the boundary of that space-time. And entanglement plays an important role in determining the structure of this space-time. Thank you.
Now we have time for some questions, and there's a procedure for the questions to ensure that people who are watching by video can hear us. There are runners with 3 microphones. The microphones have 3 colors. I think they're, I don't know, purple, pink, and orange. So if you raise your hand and hold it up long enough for the microphone to come to you, I'll call on you by the color of the microphone. Please stand up, purple, and tell us your name, and tell us if you're a member, and ask a question.
It's okay. My name is Chris Sorensen. I'm a member. And,
I need you to talk into the mic because it won't get recorded if you don't.
okay. Anyway, you mentioned the gravity wave detectors.
Yeah.
What kind of experiments are planned for those, and what are they looking for?
Well, these detectors are currently detecting, again, trying to see gravity waves. And the gravity waves can be produced by these 2 black holes orbiting each other, or 2 neutron stars. They have to be very heavy objects moving relatively fast. And so those are the 2 things that have been observed, collision of 2 neutron stars and collision of 2 black holes. And in the case of the collision of the neutron stars, they also saw the light and other forms of radiations coming from the collision. So, I mean, through other observations, through astronomical observations, gamma ray observations, etc. And these have different goals, and they you can get a lot of physics from them. So you can, first of all, test the theory of general relativity, see that it is correct for these very strongly deformed spacetimes. You can try to find out how many of these black holes were there, how they were formed, what kind of stars formed them. You can study the physics of neutron stars, the type of structure that neutron stars have, and so on, have some imprint on the gravitational waves and also other signals that they can give. And also you can study that, you can view them as standard candles or things whose brightness you know, and use them to measure the expansion of the universe. So that it can be used for many things. And people keep coming up with new ways in which you can use these observations. This just gives us a whole new way of looking at the universe, not through electromagnetic radiation, but through gravitational waves. And gravitational waves can go through matter. They are not blocked by anything, basically. And so it's an interesting, very interesting area in physics now.
The orange microphone, I think that's Mr. Wilson there.
Yeah. Hi, Professor Maldacena. Joe Wilson, a member of the Society. At first, I was thinking, when you were talking about information as being a problem with black holes, there was supposed to be a big argument between 't Hooft and Susskind and Hawking on that question.
Yes.
I'm wondering if there's any indication, this question about information, that indicates whether or not, does that tell us that wormholes are not just theoretical constructs, but that they may in fact actually exist?
Well, this discussion, I guess, that was popularized in the book that you're referring to. It was basically people trying to understand whether quantum mechanics and black holes were compatible with each other or not. And all these developments I talked about in the last part of the talk were were obtained by thinking about this type of question and by trying to answer this question. And if you believe in this duality between the fixes in the interior and the boundary, then the answer is that black holes are consistent with quantum mechanics. But there are still some questions that remain about the interior. Now, whether these wormholes are theoretical constructs or not, for the moment they are theoretical constructs. No one has traveled through one of these wormholes. But people are thinking of building some highly entangled quantum systems and exploring how to send signals from one to the other and so on. And there is a process called quantum teleportation that I didn't discuss, but there's some way of using entanglement to send quantum signals by using classical signals. So you send the classical signal, but the quantum signal somehow goes in a mysterious way between the two sides. And the picture here is that the quantum signal really goes through a wormhole between the two, helped by the classical signal. That's a little bit related to something I didn't talk about, which was the way to rescue Romeo and Juliet. So Romeo and Juliet can be rescued if one of the members of the family measures one of the black hole and sends the classical information to the other family, to the family. They have to make pieces a little bit to send the information, and if they do that, then they can rescue. So the other family can do an operation that rescues both and takes them out.
I have a question.
Dale, you're not up yet. You have another question before you.
Hello?
Carl?
I have a question about entropy.
Yes.
In entropy, there is a loss because of age and expansion. That's what entropy is about. So if it expands, as the universe has expanded, there is a greater number of elements that appear and a greater number of exposures. And those exposures themselves increase the total number. And it's as knowledge grows, knowledge expands, and it expands on itself because there's greater exposure and greater opportunity for expansion. So the question is, if things expand and entropy sends more and more items, the total structure, because of its exposure, is greater than where it started. So what's the problem with entropy not recognizing that an expansion increases the total volume?
Well, you're talking about the notion of entropy in an expanding universe, such as the one we live in. I was here for simplicity thinking about the entropy of a localized system, let's say a black hole, in a universe that far away is not expanding. So these curved universes I talked about are not expanding far away. They are translation invariant in the time direction. So, so that makes the problem more similar to problems we can deal with in a lab, right? That we collapse, we can put some matter together, it will have some entropy, and we put a little bit more matter, the entropy increases. So the same type of problems we have in the lab, where we have a fixed space-time outside the experimental setup. Here the experiment was making black holes, the theoretical experiment we were thinking about. There are other issues that arise when you have cosmology, and in cosmology the main, well, there are different ways to thinking about the entropy. So you can think about the entropy density of our universe, and by summing up the entropy contribution from various sources. So there is gas, and there is stars, and there are black holes, and actually the entropy of the black holes dominates. So the entropy is the biggest thing, but you also have to include the entropy of the cosmological horizon in principle, and that's the biggest of all.
Carl.
Hi, Carl Merrill, a member of the Society. What's really exciting to me about this presentation is the melding of quantum mechanics and Einstein's theory of relativity. But the presentation was in terms of the black holes, but I've seen people extrapolate that to our very universe itself, and I wondered if you could expand or expound on that.
Well, I think I phrased it in terms of black holes because, well, the black holes are reasonably concrete, and it's a problem where we can say things more confidently, and where there was a lot of research and fairly solid results. If we wanted to extrapolate it to our own universe, that's more speculative, and we don't really know whether it is possible or not to have a similar theory. So, but let me say what the flavor would be. So if you have an expanding universe and it has expansion with constant acceleration, then it will have a boundary in the future. So that boundary that we were putting at the some kind of spatial direction in the case of the negatively curved spaces for an expanding universe that really has positive curvature, it would be in the future. And so the idea is that there could be a theory that is defined in Euclidean space without time, and that correlations and so on and the statistical measures that are defined by that theory agree with the ones that you get by introducing a time and then evolving things in time, generating that same statistical distributions by thinking about the time evolution. And, but we don't know. There are some examples of theories like this, but they're for very weird theories. They're not for Einstein gravity theory. They're called for some, they are true for some theories called higher spin gravity, are very weird and complicated. But the fact that these two theories have similar symmetries and have some kind of scale invariance and so on is useful for thinking about the physics of inflation, for example. So, it's, but yeah, we don't know whether there is a complete correspondence or not in this flavor. My feeling is that we still need to understand the rules better and better, and it might be might take a slightly different form or a completely different form.
Orange microphone.
My name is Usman. I'm visiting here from Rochester, New York. My question to you is specifically about string theory. For any scientific model to be trusted, the theorists have to come up with an experiment or at least a parameter that could be measured, and then the theory could be subsequently falsified, or at least be made distinguishable from any competing ideas. Has string theory until now given any such parameter? For example, a version of Bell inequality in quantum mechanics, or a similar version of some test that one could do? Or if not, is there any chance in the future that such a falsifiability test could be made?
Right. So the experimental part of the talk finished when I said that I move into the theoretical challenges, right? And then the way I presented it, I used string theory as a candidate of a theory, not tested in nature, and it has not been tested, that this can put together quantum mechanics and gravity. So at least as a theory that describes quantum gravity in our own real world, string theory has not been tested. But this relationship I'm talking about relates string theory to other systems. And so, for example, the theory of quantum chromodynamics, the theory that describes strong interactions, contains strings. And these strings are routinely produced in particle accelerators. And they can be viewed, the standard view of them is that they are created by quarks and antiquarks, and there is a color electric field going between them. But the idea is that in a theory where you have a large number of colors, these strings which are made with gluons can behave as fundamental strings moving in some higher dimensional space. And so that's the higher dimension that the particles were living in, I was talking about. So you can find some theories that are similar to quantum chromodynamics, that are small, let's say, changes compared to quantum chromodynamics, where this relationship to a higher dimensional world can be tested, can be checked mathematically. So the relationship I talked about, this aspect of string theory I talked about, which is the relationship between the boundary theory and the bulk, is a mathematical relation that you can check and test mathematically. It's a hypothesis, but you can derive its consequences and check it mathematically. And it might be that this relationship is useful not for quantum gravity in our own world, not for the gravity of our own space-time, but it might be useful for thinking about strongly interacting quantum systems. And then they are equivalent to a gravity in some other universe that they give rise to. Okay? So, and that I think is the more promising way that these ideas could be tested, because you could make systems of strongly interacting particles, and then you can check that they behave as if they were described in this higher dimensional space-time. So testing quantum gravity in our own real world is, well, further would involve, I mentioned that the Planck length is very tiny length. So to test it in our own real world, the best hope perhaps is cosmology. And one idea for seeing some effects related to strings, well, there are various ideas people have proposed, but one of them is to look at the non-Gaussianity. Well, maybe I don't want to get too technical. One of the current areas of research is to understand the primordial fluctuations. So these are fluctuations in the cosmic microwave background. That's one way to see them. So these are some fluctuations. They have some statistical distribution. And deviations from this statistical distribution, which is to lead in order is Gaussian, but if you have some deviations from Gaussianity, can imply the existence of new particles that were present during the inflationary stage. And if those particles had spin, for example, they imprint some very special patterns that would be evidence of these higher spin particles that are common in string theory. So that's another way you could see something. But my feeling is that probably we need to understand the theory better to have more, well, predictions that are easier to test.
So 3 more questions, pink, purple, and then orange.
My name's Jim McCormick, and my question is about these constituent components of space-time that you alluded to. I think you said that they're, at the event horizon, they're analogous to string theory, And in fact, they might involve something like negative energy that looks like negative energy to one policeman, and it doesn't look like negative energy to a different policeman. And I'd like to invite you to maybe speculate further. First, maybe I got it wrong, but if you get away from that event horizon, does that give us some insight into those fundamental constituents of space-time?
That picture with the negative energy and positive energy is just the picture we get in quantum field theory, so standard quantum particles in the space-time geometry, in the black hole geometry, right? So that, I would say, is the standard picture that Hawking used for deriving Hawking radiation. The more string theory approach and so on, that was necessary to explain the full entropy of the black hole. That cannot be explained, at least in a way understood so far, in terms of just quantum fields in that space-time. And that involved going to infinity and replacing going to a region very far away, and then replacing the whole space-time by these particles that were living on the boundary. And I think that relationship was discovered in the context of string theory, but it might be even more general for any theory of quantum gravity, whether it's string theory or not. We don't have any other very concrete examples for other theories. But,
my name is Jim Griffin, and I'm a member. I take space-time to be the world we live in, including gravity.
Yes.
Is that correct?
That's correct, yes.
And so do I understand it that if we take a boundary of our space-time and put particles there which have no gravity but obey the laws of quantum physics, then by properly arranging those boundary particles, we could reproduce the space-time that we see, including its effects of gravity. Is that correct?
No. And it's not correct because this, so it would be correct if we lived in a space-time with negative curvature, if we lived in so-called anti-de Sitter. It's not true for an expanding universe like we live in. So it depends on how much you want to assume. It could, in principle, be true in a universe that was similar to ours, but was not expanding. Right? But what you said was correct. Would be correct for that universe.
Okay, but I guess I thought I heard you saying that if we take the boundary and use the quantum theory.
Yes, for those universes. So understand.
And then make a correspondence between that theory and a five-dimensional theory.
Yes.
That then the interior would be space-time.
Okay. So this is an equality that can be applied in different ways. So it's like a bridge connecting two theories. So if you want to describe it for our own space-time that we live in, that is expanding and so on, we don't know how to do it. I was asked this question before, and I said that I only speculated that perhaps in the future there is some theory. Now, if we change just slightly our space-time, we can have the same matter and everything we have in our space-time, but we imagine we live in a negatively curved space-time, so it could be very close to flat as it is here, but then has negative curvature along distances. Then, in principle, there should be a theory living at the boundary. So those other particles without gravity is an equivalent description to the one we would have in our own space-time.
Okay, thank you.
We think it should be, but we don't know the concrete correspondence for our own space-time.
Yes.
Yeah.
Last question, Bruce.
Yeah.
I'm Bruce Murie. I'm a member. What is quantum gravity? I always thought it was a competing theory to string theory. Is it now part of this theory that you're talking about?
No, well, quantum gravity is just the quantum mechanics of space-time. So it's gravity quantized, right? And yeah, I think I normally use this name for describing the general process of taking a theory of Einstein theory and then quantizing it in some way. So I view string theory as a candidate theory of quantum gravity. There are other people who have other candidate theories, like something called loop quantum gravity, for example, which is what I think you are referring to. Yeah, so these are, this is another competing approach, which, but I was referring just to the general process of having a theory that describes the quantum mechanics of space-time. So it's not a concrete, so when I say a theory of quantum gravity, I mean some theory that describes the quantum mechanics of space-time in a consistent way. you pick your favorite theory that describes quantum gravity. So in the same way that quantum field theory is a theory of quantum interacting particles, and you can have different kinds of quantum field theories.
Well, thank you. But before you go,
Okay, thank you. Thank you.
I'm going to present you with this framed copy of the announcement of your talk.
Thank you.
And a signed copy of the volume 1 of the Bulletin of the Philosophical Society of Washington.
Okay. Thank you very much, and thank everybody.
So before you go, a few housekeeping announcements. Just a reminder that PSW is a volunteer organization, and we depend on our enthusiastic, active, and capable members and supporters and sponsors to keep this organization going. So if you are not a member, please join, and if you are a member, please consider contributing more and or becoming more active in the organization. You can apply for membership on the PSW website, which if you haven't seen it, we now have a new website. It's a big improvement over the old one, and there's a blue join button at the upper right-hand corner of the home page, and when you press that button, you'll pull this page up, and you'll see the membership application button, which you can press, and when that will pull up an application form, fill it out, pay your dues, you'll be considered for membership, and in all likelihood, you'll be admitted, and in the very unlikely event that you're not, we will refund your dues. So please join. Remember that PSW is a 501c3 educational organization, and your donation is tax exempt to the extent permitted by this year's laws. I don't know about next year, so you better give soon. Next lecture will be on Dragonfly on September 21 at 8 p.m. right here in the Powell Auditorium. And the speaker will be Zibby Turtle, and she'll be speaking on the proposed Dragonfly mission to explore Titan, study its chemistry, and look for signs of life. Biosignatures, technically. Zibby's a planetary scientist at the Johns Hopkins Applied Physics Laboratory. She's the principal investigator of the Europa imaging system on Europa Clipper and principal investigator of the Dragonfly mission. Concept, currently in competition under NASA's New Frontiers program. She primarily works on remote sensing observations and numerical modeling of impact cratering and tectonics on planets and moons, and she studies the lakes and weather on Titan. Other upcoming lectures include Charles Norton of NASA speaking on CubeSats, Jim Garvin and Melissa Traynor of NASA Goddard Space Flight Center on Venus and why we need to go back to that planet. Franz Cordova, the director of the NSF, and Lee Cronin, a very creative and interesting chemist who holds the Regius Chair in Chemistry at Glasgow University. So I think that will be a fun talk. The social hour ends at 10:30, after which PSW members and guests meet at the Fairfax Hotel Lounge just across Massachusetts Avenue. If you want to join us, please speak with corresponding Secretary Robin Taylor, Membership Director Lloyd Mitchell, or me. Please use the side entrance to exit the building, and I will now accept a motion to adjourn the 2,396th meeting of the Society to the social hour. Second? All in favor? All opposed? Meeting is adjourned to the social hour.